Hello, everyone. The title of our paper is SSVOD, Semi-Supervised Video Object Detection with Sparse Annotations. I am Tanvir Mahmud. My co-authors are Chun-Hao, Burhaneddin, Yaman, and Marculescu. I am from the University of Texas at Austin. Let's introduce the problem. Supervised video object detection requires dense annotations on several time steps of videos. So in figure A, we can see the supervised method requires annotations in several time steps. But with sparse annotations, the supervised method generates suboptimal performance for insufficient temporal exploration. So when we have only two-step label frames over the video, we cannot explore different time steps in the supervised method. But the SSVOD leverages semi-supervised techniques to estimate robust pseudo labels across different time steps by using the sparse annotations. So by using only two sparse annotations, we can estimate some pseudo labels in other time steps of the video. So that we can explore all time steps or different time steps over the video. So here is the proposed method. So we will describe every block one by one. So you can see there are two sets. One is unlabeled set, another one is the label set. So we have two sets of frames to operate in this framework. And in every set, it consists of one key and several reference frames. So you can see we have one key frame at the th second, and for other two temporal time step like at t-1 and t+1, we had two reference frames. So these two reference frames will help the key frame to predict the estimation. And we have two kind of model. One is the teacher model, another one is the student model. So the teacher model operates into the unlabeled set, the weakly augmented version of the unlabeled set, to estimate some pseudo labels. And we have some robust filtering techniques to operate on the pseudo labels. So we particularly use the flow warped feature set generator to estimate the flow warped features from every reference frame. So these flow warped feature sets are used with the original key features. So you can see we have these are the flow warped feature sets, and we also have a key feature set. So these three feature sets will be used by the video RPN and video ROI to estimate the most robust pseudo labels. And also here we can see this is a student model. The student model operates into both the unlabeled set and the label set. So it operates into the strongly augmented version of the unlabeled set, and the label set is directly used. And for the unlabeled set, it uses the pseudo labels that is produced by the teacher model, and the teacher model is using the weakly augmented version of the unlabeled set. For the label set, we directly use the pseudo labels from the annotations. And here's the flow warping technique for generating the feature set for every reference frame. So you can see that here we use the flow estimator that extracts the motion map between each key reference pair. So you can see there are two key and reference pair. Firstly, we estimate the motions using the flow estimator. And after that, feature warping is carried out on each reference feature. So in every reference feature, we apply some flow warping with these kind of motion maps. And that helps us to estimate the flow warped key features. So this helps us to map the reference feature to the key feature. So in every key reference pair, we can map every reference frame feature to its representative key feature. And then what we do, we actually we replace the key feature. So we replace the key feature that is in the middle with the flow warped feature set of the reference feature, so that we can have the flow warped feature sets. So now we have two sets of feature. One is the key feature sets, another one is the flow warped feature sets. And we will use these two feature sets to estimate the robust pseudo label. And to estimate the robust pseudo label, we have two types of filtering method. Sorry, we have three types of filtering method. So one is the cross IOU based pseudo bounding box selection. Another one is cross divergence based pseudo hard class selection. And the third one is the confidence aware pseudo soft class selection. So first we check the cross IOU based pseudo bounding box selection method. So we particularly use the cross IOU estimation from object pair matching between the keyframe prediction and each flow warped keyframe prediction. So there are two kinds of prediction that we said before, and we use the cross IOU estimation across different objects of these two predictions. And the pseudo bounding boxes with high overlaps, that is high cross IOUs, represent the most consistent estimations. And we filter out the most consistent bounding boxes that represents with high cross IOUs. And then we have a cross divergence based pseudo hard class selection method. So in some cases, the bounding box estimation can be very accurate, but the object class is wrong. So we have to find out those object classes that has those bounding boxes that has false object classes. And the hard class label on the bounding boxes with this kind of inconsistent classes can lead to false estimation. So we estimate the mean cross-scale divergence for each object present in the key and reference frames. And the bounding boxes with a lower KL divergence across these predictions are filtered for hard class labeling operations. And finally, let's go to the third selection approach, that is the cross-confidence-aware pseudo subclass selection method. So here, to enhance the exploration of the generated pseudo labels, several class predictions from remaining bounding boxes are filtered out for subclass distillation. So such distillation increases the robustness on object class predictions. So we do the distillation on the remaining on a set of remaining predictions from the teacher to the student. So use the teacher directly use the teacher predictions to do the distillation to the student prediction. And then we do some comparison to the supervised baseline. So there are 3 supervised baseline. One is trained with single labels frame per video, and others are 5 and 15 labels frames per video. And our SSVOD is trained with single labels from keyframe per video, but we do use some pseudo labels from other surrounding frames. So you can see the supervised performance greatly depends on the availability of annotated frames per video. So you can see the supervised performance drops significantly when we reduce the number of annotations from 15 to 1. But our proposed SSVOD reduces the performance gap between this sparse annotation, that is 1 frame per video, and to the dense annotation between 15 frames per video. So we can see by using the SSVOD, we can achieve almost the same performance of the supervised 15 frames per video by using only single label frame per video. And here are the main results. We do some performance comparison on the ImageNet bit validation set under single label keyframe per video setting, and also under multiple labeled keyframe per video setting. So we can see that we used different baseline methods for comparison. So the SSVOD achieved the best performance over all the baselines. So in summary, the SSVOD significantly outperforms the image-based methods, the naive integration of supervised video model with some semi-supervised image techniques, and also some several baseline video methods that was primarily built targeting the image-based operation. And we do some ablation on loss components and pseudo labels. So you can see we have 3 types of pseudo label selection method, and we introduce 3 loss functions to optimize these pseudo label selections. So you can see integration of each components of the proposed 3-level pseudo label selection method contributes to noticeable performance improvement, and we get the best performance by combining all 3 methods of pseudo label selection. And we do some ablation with various baseline model for the VOD task. So you can see we have 3 model, that is FGFA, SALSA, and Troy. So our method can integrate any baseline baseline model. So our SSVOD scheme provides consistent improvement over supervised baseline across various baselines. And also we do some additional comparison on benchmark dataset. So SSVOD achieves consistent improvements on 2 other benchmarks, that is Epic Kitchens and YouTube fees. So we can observe the similar improvements on other datasets that represents the robustness of our proposed framework. And finally, we represent some demo that is a qualitative results. So we do the comparison mostly with the supervised baseline. So you can see the SSVOD demonstrates better temporal consistencies predictions compared to its supervised counterpart. So as the supervised method cannot explore different time steps, we find like it misses most of the objects when the object is moving very fastly or when the object is very small to isolate for. So that represents the shortage of training, but our SSVOD actually introduces the temporal consistency to estimate this kind of consistent predictions. So in summary, we introduce a novel semi-supervised video object recognition framework, that is SSVOD, using sparse annotations. And SSVOD explores temporal feature space of groups of frames to search robust pseudo labels based on motion consistency. SSVOD achieves around 98% of densely supervised performance by using over 95% sparse annotations. Thank you for your patience.